Hi, everyone. So first, before we get started, I want to thank Adolfo, who co-proposed this talk with me. He unfortunately couldn't make it. He's in Barcelona right now. But he did a lot of great work making beautiful slides. You're going to see they're awesome, beautifying my really ugly slides. And he contributes a lot via his work on ROS Control, and also he's added a lot of great ideas and design to the ROS2 work that we've done. So thanks, Adolfo. I just want to get a temperature reading on the audience. Who here has worked very extensively with a real-time system before? Awesome, OK. Who here has not, but is familiar with the concept? OK, that's almost, who here has no idea or has heard this buzzword a lot, but actually doesn't know and doesn't know the definition? OK, great. I'm going to start out with kind of a concrete example with a situation that we're all really familiar with, which is making a robot do something. Then this is kind of the motivating use case for ROS Control. But we're going to kind of extend this, and it's not going to be specific to ROS. Yeah, you have a robot and you want to make it do something. You want to make it execute a simple position trajectory controller. And you wrote some code on your desktop, some controller code. And when we expand what this looks like, nice. It's composed of many separate software modules that are independent, and they may have been written by you or someone in your lab or company, or someone who distributed it, you've never met, it's open source, whatever. And you can kind of break down your controller into an abstract action interface to manage the logic and inverse kinematics. You might want a different inverse kinematics algorithm. It varies on your robot geometry. Signal interpolator is that green thing, PID feedback loop, and these modules all have they're like functions with certain input and output. But that logic isn't necessarily tied to their execution logic and their performance requirements. That might change based on your application. Kind of scoping out again, we might want to also do something like change our controller during execution, during runtime. So for example, we were doing a position controller before, and now we're doing kind of an impedance controller. And it would be nice, if we could decide we're doing something else without, resetting the robot, without doing significant work or having a significant penalty on our execution, switch out this controller. So the system topology can change. That would be cool. And on the other side, we kind of see the same story, but with hardware, with the hardware interface to the robot. So this is kind of an awesome diagram with this is gravity compensation. This is your traffic speed limit, which is your joint limiting. These, gearboxes. This funnel is a filter. But you have these interfaces to the different components of your robot. Maybe you have a ClearPath robot with a Baxter and the mobile base, and you want to swap that out. So if you had these kind of composable components, you could maybe also you're doing the DRC and you have different grippers for Atlas. It'd be cool if on runtime or during runtime, very easily you could switch out that gripper. But tying it back to the topic, the title of this talk, again, some of these blocks, and especially on the hardware side, are going to be subject to real-time constraints. Cool. So you guys apparently all know what this is, so I'm just going to skim through this so we're all on the same page. Maybe our remote viewers don't know, or someone's consulting this talk to learn about it. So people often conflate real-time performance and low latency. But the definition of real-time performance is that you're deterministically meeting a deadline, and that if you compute something after you've exceeded your deadline, then that is an error, or that is incorrect data. And often latency and real-time performance are actually at odds, because you may need more time to deliver the correct data. And if you're trying to get a low latency system, you're going to exceed your deadline a lot. kind of a nice visual representation of this, some terminology. The deadline is often, this desired like constant update rate, and you're going to have an allowable margin of error, which is usually called the jitter. And some people call like exceeding the jitter overrun. So there's also different kinds of real-time categorizations that depend on your use case. And that they're often defined by what you do with the data after you've exceeded the deadline. I guess another show of hands, who here has worked on a hard real-time system before? That's most of the people who raised their hands initially, so cool. You guys are pros. So yeah, a hard real-time system is when if you miss a deadline, that's system failure, go to a failure mode, something is really bad. And that's really important for systems where there's a lot of money or like human lives on the line. If you have a malfunction in your nuclear reactor, it could be really bad. If you miss a data packet on your autonomous satellite, you're going to go out of orbit, stuff like that. A soft real-time system is one where you're tracking, you're meeting your deadlines, but you don't necessarily throw out the data after you're aware that you missed a deadline. For example, you might be watching videos on YouTube and you start missing a lot of frames, then the player might adapt its quality of service to that situation. So it may give you more best effort quality of service to deliver you more cat videos or whatever you're watching. And everything in those spectrum, right? So the third category is firm real-time systems, where you may miss a deadline, and you're going to discard that. Do you want me to stop like moving around? Okay. Thank you. So you miss a deadline, and you're going to discard that data sample that you calculated instead of publishing it to another node that's going to process that data, or instead of reacting to it in some way. But you're not going to cause a total system error. So I like this very concrete example here where you're making an autonomous assembly line, you're manufacturing your green squares, and you sense that you've missed a deadline. And that means you could have made an error in your assembly line. Something could be wrong with that product, but you don't have more quality control. But this is a kind of automated quality control where when you miss a deadline, you discard the object and put it in the discarded red triangles box. So, take a step back from all this theory. Why do we care? Since a lot of people in this room have worked on real-time systems, and we've heard people talk about it all day, I think you guys all know why we care. It's really important in robotics to know how to deal with time-varying data. And especially if you're going to make a system that's reactive, that's going to adapt quickly, and controllers that are going to adapt to variations in this unstable dynamic system, you kind of need to be able to process data without missing deadlines. And you're going to need to profile your system to know what the maximum allowable latency you can have is. So this has all been very high level, but this is ROSCon, and I'm talking about ROS2. So we really want ROS2 to be real-time safe. We want it to not get in the way of your real-time system. So how are we going to accomplish that? Well, these are some tricks of the trade and best practices. So I thought I'd go over them to give you all an idea of what I've gone through implementing the system and what people who have implemented real-time systems before could do. First, you need to pick your operating system correctly, and the default scheduler on Linux is not considered real-time safe. It uses a non-deterministic scheduler that optimizes for fairness instead of determinism or priority. Right? So RT preempt is a kernel patch which changes Linux threads to be fully preemptible. And that's kind of considered soft real-time performance because you can get real-time-like performance, but there's nothing built into the kernel to fail when you sense an exceeded deadline. In fact, the kernel has no concept of an exceeded deadline. That's at your code level. I've listed some other solutions on this slide, mostly so you can Google them later. I'm not going to talk too much about the proprietary solutions because we're an open source company. But we like the POSIX interface, so that's a big plus. And the fun fact, the standard library in C++, the thread library in C++11 doesn't expose some important things I'm going to talk about, like thread scheduling. So as I said, the default thread scheduler on Linux, not real-time safe, and as well as the way the kernel handles threads. But even after if you select RT preempt as your operating system solution, then you have to choose your scheduler correctly. You need to choose a deterministic thread scheduler, like FIFO, round robin. Deadline is kind of a newer thing in the newer Linux kernel, 3.18 or something. And you need to choose a high priority level. The priority level is how the deterministic scheduler determines which threads can preempt others. And you want your real-time thread to be preempting all the other threads, which are not as good. Is that a question, or are you just using? OK, thank you. So scheduling is not the only kind of hidden danger we can run into. The default heap allocator in most systems, and any major operating system I can think of, is not deterministic, or it may incur prohibitive penalties on your performance, which is why usually people making real-time systems avoid heap allocation during a critical section, during real-time execution. There are alternatives, like an O of 1 allocator is usually a memory allocator that is deterministic or runs in a known constant time, which you can profile. And you can know your memory allocations will only take that amount. But I'm not going to talk too much about those today. There's any time when you're doing multi-threaded code and you use mutexes or locks for a shared resource, then you could run into a situation where you block for an indeterminate amount of time on that thread, on that lock that's protecting the shared resource. Because you don't know how much another thread is going to need, how long that other thread is going to need for that shared resource. And also, there's kind of this danger of deadlock, be really bad. There's a category of dangers where anything where you're blocking on a response from a physical device is generally means that you're going to incur a large latency penalty. So printing to the screen is one. If you block on sending a network packet, like TCP does, then you're going to be waiting for that packet to crawl through Ethernet cables. It's going to crawl through like the whole stack of the internet, maybe. You're not really sure. So you don't want to block on a network call. And kind of, in general, any device driver where you're blocking on a response. So accessing the hard disk is another interaction with the physical device, which is common and often not transparent to a user or a developer. And I mentioned this with the heap allocator, but I didn't go into too much detail. So when you swap memory from RAM into main memory to make more room in your RAM for memory you're requesting, then you could incur a very large penalty. There's a lot of unknown stuff going on to you, especially if you're writing a portable program to the operating system when it's retrieving or when it's writing the memory from RAM into main memory. So you don't want to do that. And actually, what I just described is called a page fault. It's called a major page fault, actually. So that's kind of the word that people will use. You don't want to have page faults in your real-time execution phase. So I think now we're ready to talk about the design choices that we're making in ROS2 to kind of facilitate an easy way for you to make real-time safe code. And to motivate this, I've illustrated kind of a broad illustration of the different libraries that interact with each other or don't interact with each other when you write ROS1 code or ROS2 code. And you don't need to know all the details here, but it's kind of the different choices you can make in your one program. So here, the green sections, the green blocks are blocks that can be made real-time safe by our definition. In ROS1, I've also omitted Python because there's a lot of problems with Python for this application. In ROS1, people rely on these external frameworks for real-time safe execution. ROS CPP, the implementation is not considered real-time safe. TCP ROS, definitely want to avoid that, as I just said. UDP ROS, maybe good, but again, there's a lot of problems we've gone over with UDP ROS, and also it's blocked by the fact that it's baked into the implementation. It's built into the implementation of ROS CPP. It's not modular. So the improvement we're trying to make in ROS2 is that any path you can take through certain stacks, it's configurable. You can make the client library, the equivalent of ROS CPP, real-time safe. And as long as you choose your middleware and your operating system correctly, then you can be successful in some kind of real-time execution. So how do we make things configurable? We make them modular, right? There's kind of an idea where, we've mentioned the executor a few times today. The executor is this way of taking out the scheduling of your program, separating it from the logic of your node. By inserting the logic of the node into the executor, which handles the scheduling of tasks you need to do, then you've separated those two components. And we're taking a similar strategy with memory management, which I'll go into a little more detail. This is a very simple kind of cartoon of the implementation of spin in ROS2. It's a function of the executor. And in the real-time case, you're going to have these phases, right, where you pre-allocate all of the memory into these pools. You deallocate them when you're done. When you're spinning, you consult those pre-allocated pools of memory if you need to allocate some representation of an object. And kind of on the topic of synchronization and blocking, you block to wait for work to come in asynchronously, like you're waiting for your publisher you're subscribed to send a message. And you block, but you're going to block with a timeout. You're going to wake up, and if nothing came in, you're just going to say nothing came in. But I'm updating, so it's OK. You can block indefinitely, but again, we're not going to do that in this case. So the blocking is handled by the DDS implementation. And that allows us to say, if we trust this DDS implementation to be real-time safe, and it should be because that's actually a part of the spec and what it's kind of built for, then this blocking is fine. So the way we handle this, we specify this pre-allocation strategy is to the constructor of the executor. Optionally, you can pass an object that's called a memory strategy. And that memory strategy owns the pre-allocated pools that you use for real-time execution. But by default, it has no state, and it just calls new and delete when the user wants to new and delete something. Oops. OK. So that comic I just showed you maps kind of nicely to this idea of node lifecycle. Essentially, this came up in the talk. Someone asked a question about this, where, do you want to write a custom main or not? And for real-time execution, it would be really nice if instead of, saying, all right, I've got this initialization phase, and then I call spin, and then something happens, and then we're out of spin, and then we're in the teardown phase. Then instead, we have this defined API and this defined state machine, where all you need to do is write what the executor does and the subscribers and the publishers for your node. And we're getting inspiration from these existing frameworks that a lot of people in the ROS community use. So we're actually actively designing this right now. So this picture could be subject to change, but it's kind of the basic ideas, which is pretty easy to understand. You have a state machine. You create your node, and on each transition in this diagram, this is kind of a message, right? It's either a function or it's a service call, and there's some kind of callback that happens. So you say, I'm initializing my node, or I'm creating my node, and this is my user callback for what happens when I do that. And in a real-time execution context, that means, I'm in on create, and I pre-allocate all of my pools of memory. Inactive is kind of a state where you are not doing anything, but you are constructed. All the objects are in memory, right? But you could be reconfigured, so some of your parameters could change, you being the node. Active is the only state where the information you're producing as a node is valid. In the other states, these are kind of configuration states that are saying, I exist, but I'm not doing anything that's relevant to the correctness of my program. And parallel to created, we have a state that's on destroy. So customizing that is kind of like a bit like customizing having a custom destructor for an object. And also, you might want to be able to react to errors, kind of, going back to in hard real-time systems, if you have an error mode, you want to reset if you reached an exception. So the takeaway for this is this abstraction is really nice if we want to denote this as the only real-time safe or real-time critical section of our code. And it also has a lot of benefits besides real-time safety for anyone in this talk who's totally not interested in the subject at all. So going back a little to our original example, we talked a lot about composing nodes. And I'll go into a little more depth about this right now. So one connection to node composability and what I just described is that when you compose several nodes in the same process, a potential benefit is that you could sync up their lifecycle because their execution is kind of tied to each other. As I said before, there's this nice separation of execution and logic, and there's also a performance benefit we get because we really care about performance in real time. And that's the shared inter-process pipeline that William presented. So the idea with node composability is if you put many nodes in the same process, then they can take advantage of this pipeline. So speaking of communications, I wanted to illustrate the different kinds of ROS2 communications in the context of their real-time safety. So it kind of is like the more locality that you have in the two nodes or entities that are talking to each other, the more determinism you have, and vice versa. So inter-process and between device communication, there's this extra distance they have to travel, and there's more chances for non-determinism to rear its ugly head. But luckily, DDS has a lot of stuff we kind of get for free, like quality of service, that make inter-process and inter-device communication kind of soft real-time safe. Again, the in-process, intra-process pipeline is really helpful for us because we can avoid incurring penalties on copying memory. But coordinating the shared access to these shared resources also could introduce non-determinism. As I said before, synchronization primitives, mutexes, locks, they're all tricky to coordinate, unless you do it in a lock-free manner. And the simplest and easiest thing to do is say, I have these variables in a thread, I have a class, it shares memory, I don't need to worry about other threads accessing it. But again, that's very simple, and it might not be suited to your use case. So, the update on where ROS2 is today. Basically, we've worked a lot on memory allocation and making ROS2 configurable so your executor can have real-time safe memory allocation through having a kind of memory pools that are allocated on the heap beforehand, then you need to have a hard limit, a known limit on the entities that you're going to publish and subscribe to. And Morgan actually mentioned this in his talk about free RTPS, because you can't dynamically grow the size of the memory that you're using in the real-time safe section. There's also a current limitation where the messages have to have a static size, so we can't use things like strings. But Adolfo actually has some really interesting ways of getting around that. So, what's coming up for us? We talked a lot about component lifecycle, and that's kind of the biggest next thing we're going to tackle, as well as, and kind of goes hand in hand in that, is the node composability. And there's actually kind of a caveat with the intra-process pipeline right now, is that it's actually not real-time safe because it uses mutexes, standard mutex. And so the alternative to that is implementing it in a lock-free way. So anyone who's not familiar with lock-free programming, really quick, it's kind of like, instead of waiting in line to go through one door that one person can fit through, it's like using a revolving door. Think about that. So to go over why this is a good idea, we're going to use a specific example, which is ROS Control, because that's what a lot of people in this room are familiar with, and Adolfo is the creator and maintainer. So basically, ROS Control does these first two things, and it does them really well. It does not do the third thing, and it's an often requested feature, actually, but it would be very difficult. It is difficult for Adolfo to implement this in ROS 2 right now. So ROS Control, no node composability. But as we saw in our example, it would be really nice to have that. For something like ROS Control, where there are many blocks in your system diagram of what your controller is going to look like. Adolfo did this great kind of data analysis on his code base and saw that 55% of the code base, 25 plus 30, is dedicated to things we're planning to do natively in ROS 2. So that means that when ROS Control gets migrated to ROS 2, it will be half as big. And that is a big win, and it makes Adolfo's life a lot easier as the maintainer of this repository. So I may have mentioned earlier that I did benchmarking on all these claims that I'm making in the presentation, and I'll just talk a little bit about them. This is the setup that I made. It's an inverted pendulum simulator, and the inverted pendulum is kind of this classic difficult control problem that is also, it's like a simplification of a humanoid walker. This is kind of the schematic. We don't have RQ2 yet in ROS 2. I guess I could use the bridge, whatever. We have a PID controller and a simulator, and these are two separate nodes kind of to motivate when we have node composability. This simulator could be swapped out with a hardware interface to a real pendulum. We also have two non-real-time processes that are interacting with the real-time process. One for teleop, so if the user wanted to type in a command, an angle for this pendulum to balance itself at. And we have a logger, which does operations I said were non-real-time safe, like console output and recording all the benchmarking results to hard disk. So more in-depth technical details, I used RT preempt, which is, again, the Linux kernel patch, not a hard real-time system. I chose a round-robin scheduler and thread priority 98 because thread priority 99 ends up clobbering some important systems processes, which is really bad. There's a nice trick where you can replace the malloc call, which was really helpful for tracking mallocs and heap allocations made on the real-time execution path. And getar usage is a system call on Linux for tracking resource allocations for a particular process. So kind of the goal that I've set for this system is a 1 kHz update loop with 3% jitter. And this is kind of a golden standard that we hear a lot about in robotics, basically based on how fast your motor can update. Oh yeah, and you can see the code on GitHub. Whoops, spoilers. So I'm happy to report there were 0 runtime allocations. And the way I figured this out is that my custom malloc basically looks at this global Boolean that gets set to true. It's kind of faking the lifecycle. This is like the active stage. So if it's active, then we just throw an error. And we never see that exception when we're running the benchmark. We also see 0 major page faults because I collect the page faults on every iteration of the loop. And there's some minor page faults. Minor page faults are when the address in RAM isn't yet mapped into the memory management unit. But as you'll see in the next slide, the penalty incurred by that is OK. It's OK. So this is a time series of the latency, where the latency is the time between the last 2 execution iterations minus 1 millisecond, our goal. And I've highlighted with the dashed line what our acceptable jitter is. So you can see, I hope you can see these lines. There's one instance of overrun. And that instance is 3.5% of our update rate, which is 0.5% above what we said our allowable jitter was. And this histogram is just to give you an idea that the mean of the data is really quite far away from this data point. But again, the scale of this is really big because there's a data point here. But again, it only happens once. So you can't even see anything there. So I also had a longer run that was 7 times as long and applies some stress on the system. So stress is a really nice tool that just spins up worker threads that do stuff over and over again. So it's putting stress on the CPU and stress on I/O. So here there were 3 instances of overrun, and the spikes are a lot bigger. They're 25% of the update loop. But it's still pretty good that we're not actually exceeding 1 millisecond. And again, the histogram, the scale is still crazy, but we're like an acceptable margin away from our maximum jitter. So these results are, I think, quite encouraging. And I think they would be suited to a soft real-time system. But of course, there's still a long path ahead of us. There's a lot of features we need to implement that I went over that would be nice to have, and it would make real-time systems in ROS a lot more convenient. And we also need to audit the code for real-time safety and more features. But it's a very exciting field. There's a lot of interest in it. And if you are interested, if you want to learn more, if you want to lend your expertise working on real-time systems, then please talk to me, talk to the team, get involved on SIG and G. We'd love to hear from you. Thanks.
We've got time for a couple of questions. Peter.
For the key instances where you missed your deadline to ROS 5,
Mm-hmm.
was the source of the kernel, or you like the source of
So the question was, what is the source of the overrun in this slide? So I need to run more data to see what the conclusion is, and there isn't enough introspection to see like exactly the line of code where the latency was. But I actually think it has to do with the stress command because I don't see latency of this size when I run it without stress, basically. So as I said on the last slide, I wasn't. And again, the size of the data is different, so maybe this isn't statistically significant. But the size of this overrun, the maximum one, is 25% of 1 millisecond, 250 microseconds. And the size of this jitter is way smaller. So. Mm-hmm. Yeah. Yeah. Yeah, so he pointed out that the latency in this graph is probably due to startup. And I totally agree. There's minor page faults on the first iteration of the loop. And so those are probably interrupts that are. Yeah.
Dave.
Oh. Went in the wrong direction. So he asked if in node lifecycle these are controller nodes or just any node, right? Yeah, so we'd like node lifecycle to be available for any node. That's kind of the idea in implementing it in the core stack. So he asked if we need it in all applications. So actually, in Stefan's talk earlier today, he had a pattern that was really similar to this in one of his tools. So I think it would be useful in other applications, yeah.
In the back.
I'd like to point out that you have an assumption in there which excludes any other real-time count than RTPM. Could you go back one page to the example whether it is a flow of the inner loop where you should
This one.
That's exactly. That's the one. Now, the executor is obviously a real-time thread, right?
Is the executor is a real-time program? Is that what you said?
Thread.
Thread? Yes.
Which is real-time program.
Yes.
Now, the assumption being here that is that you might be able to use primitives from a real-time thread. And that will hold only for preempt. It takes out 10 or 2 completely from it.
Yeah.
Or any other real-time thread which is not uses the process code. So you, by using the middle way, if you have RRT, you take out all the other kernels and options, etc.
Right. So he pointed out that I've made a huge oversight in not including any other system than RT preempt, which I totally agree with. It's very important that we design for more than one platform. I just haven't done it for this initial proof of concept. But I also want to point out that this code is not specific to, like, ROS2 is not specific to RT preempt. The executor that I implemented uses pthreads, and it's kind of made with RT preempt in mind. But you could implement a different executor that uses whatever primitives are available in XenoI. We'll talk later.
In the middle here.
Sorry, can you repeat the last part? Use what? Sorry, it's a little too quiet. So you're asking if you can specify a certain deadline on the API level, like have an API call that says set deadline, whatever. So I think having such an API call would kind of break. Well, this is total opinion, but I think that would break the goal to have ROS2 kind of available for both real-time and non-real-time systems. So set deadline would be meaningless in a non-real-time system. I think that would be suitable as like a parameter that could be read by a real-time executor. And that way you can use a parameter interface to change your deadline if you wanted to, or specify that in maybe a launch file. Yeah.
Mike.
I would just say I think it's really neat, this idea of having a future where ROS Control controllers become nodes and move-based plugins. I think the most exciting bit about that for me is actually being able to see the data crossing those boundaries using visual tools. Because that's a huge problem right now, that anything you want to see in a controller, you have to bring it out inside that thread and publish as a ROS API.
Absolutely. So Mike, this is just a statement, so I'm not going to respond to it. But he pointed out that a big win with this design is that ROS Control controllers and components are kind of first-class citizens that can be introspected with tools, which is not how ROS Control works right now.
Yeah, I mean, in a sentence, the headline here is that you can call publish and you can have your subscriber callbacks invoked in a real-time safe way, which you just can't do in any fashion in ROS1 without implementing a completely parallel system. One more. Bill.
All right, so for getting the real-time errors, are you planning on exposing those through like diagnostic aggregator so that we can react based on those errors, or is that all within the node?
So I'm publishing the error as a message right now in my example. So it could certainly be published to a tool, an external tool, yeah. But it's kind of an implementation detail. Yeah.
All right, thanks very much.